It is my great privilege and pleasure tonight to introduce you to the Mars EDL team, Entry, Descent, and Landing team, who are receiving tonight our Space Pioneer Award for Excellence in Science and Engineering. We all watched it. It was an incredible thing. The previous landers had come in with airbags, but they were of a lower weight, and airbags weren't going to work for something as big as this rover. So they had to do something different, and boy, did they do something different. So to tell you all about that tonight, their team leader, Dr. Adam Steltzner, is here. May I call him up to the stage?
Steal the inputs. Indulge me in a brief moment here.
The elevator this evening. How are you doing?
Well, thank you.
Welcome to ISDC.
Thank you very much. It's good to be here. Okay. That's yours. I'll take this.
Where's your battery?
I'm in pretty good shape, and I'll plug it in
All right.
to power here. I didn't want to steal the nice slideshow that was going on.
Very nice.
Yes.
We're auctioning this laptop later this evening. Is this yours, Nancy? No, it's not. There you go. Okay. Leave it? Okay. Thank you, sir.
You're very welcome.
Welcome to ISDC.
Good evening. How are we this evening? This is Mars. You may recognize it. For millennia, really, it has captivated our interest. From before we could see it with anything but the unaided eye, we noticed a slightly more red, slightly fuzzier image that didn't move with the rest of the stars in the celestial sphere. When we finally got telescopes, we looked at it, and we were certain it was alive because we saw, erroneously, roadways and canals and airstrips and the evidence of industry. Then we got better telescopes and recognized that that was not civilization, but geology or aerology. But ever since then, we still have yet to be able to shake a sense that perhaps life exists in one of our nearest neighbors. And we hold that question in our minds for many reasons. The profound question of if we are, in fact, alone in the universe, in our galaxy, in our solar system. And a hope, perhaps, that our nearest neighbor may harbor some answer to that question. So because of that, about 7 years ago or so, we were asked to place an extremely large rover on the surface of Mars. So it wasn't just any rover, and it wasn't just any place we were asked to put it. We were asked to put it here. This is the Gale crater. It's a very large object, probably visible in these beautiful pewter globes. No, that's the moon, so that you will look long and hard before you'll see it there. Just 5 degrees below the equator, this massive crater, 90 miles across, the size of the big island of Hawaii. You can see its rim in the edge of that image. This is an image, a digital elevation map constructed from overflight data and altimetry and visual images from the Mars Reconnaissance Orbiter and the Odyssey spacecraft. You'll note that in the center of that huge crater is a massive mountain. Named after Professor Sharp, the geologist, Mount Sharp stands 15,000 feet above the surface of the crater floor. Higher, for those of you who keep track, than any other mountain in the continental US, the Rockies, the Sierras. Well, we were asked to put a rover right down there between the rock and the hard place that is the mountain and the crater. And to do that, we were going to have to do better than we'd done before. Now, if you're going to Mars, you have to do 4 things. If you're taking anything bigger than a bread box or smaller than this room, you have to do 4 things. You have to enter somewhere around 10,000 miles an hour, 10, 15. We entered at 13,320. But with enough kinetic energy that you can vaporize the spacecraft, you have to protect the spacecraft against that intense heat, shed that energy into the atmosphere. That'll slow you down, and it'll slow you down a lot, but not enough. And then at about 1,000 miles an hour, you'll open up a parachute. That'll do a good job of slowing you down to maybe 100 miles an hour or so. But that's not slow enough to touch the surface of Mars, at least with things that are bigger than a bread box. Things smaller than a bread box you can harden fairly well to high Gs. You know, we put telemetry packages inside artillery shells that'll see 30,000 Gs. But as things get big, just mechanically, it gets difficult to harden substantial engineering hardware to very high Gs. And so you're going to have to use rockets. And you'll use a propulsive system, and that'll take you down, depending on how good of a job you do with that propulsive system, that'll take you down to any kind of speed, anywhere from maybe 1 mile an hour to 10 miles an hour. And that will leave, for the last embrace, the kiss with the Martian surface, some kind of a touchdown system. Something to interface with an unknown terrain, take out that last little bit of kinetic energy. For MSL, for Curiosity, the numbers look like this. In kilometers a second, meters a second. And in terms of kinetic energy, they look like this. And you can certainly see that the vast lion's share of the energy is dissipated to the atmosphere in the entry phase. In fact, 0.03% of the arrival kinetic energy is remaining when we touch down. There's an old vaudeville joke. It's not the fall that kills you, it's the landing. That's kind of true. And for us, we struggled mightily with that last 0.01% of the kinetic energy with such a big beast. But to make it down inside Gale Crater, we had to innovate in other places as well, specifically in the entry phase. To get down there in the blue, we'd have to do better than we had done before. So this is another image of the Gale Crater. Now it's color tone shaded. Red is high, blue is low. And we've overlain the uncertainty footprints. We call them ellipses because they're elliptical. Our uncertainty ellipses of all the successful expeditions to the surface of Mars. In the 70s, Viking. 20 years later, Pathfinder. And then in the aughts, Spirit and Opportunity and Phoenix. You can see sort of an incremental improvement between Viking and Pathfinder. That was really mostly some incremental improvements in both interplanetary navigation techniques, some of which really came about by double precision computers and more computational power, and a little bit better understanding of the atmosphere of Mars. When Viking landed, we had zero clue what the atmosphere of Mars was going to be like, and so we improved our understanding. But there's a sort of a bigger jump between Pathfinder and just 7 years later, Spirit and Opportunity. And that bigger jump is really the result of a change, sort of a technological change in how we navigate spacecraft between Earth and Mars, the use of what we call Delta Door, which is the use of quasars in the celestial sphere as well-known fixed points of reference. So now the radiometric navigation was not only baselining from the Earth and our understanding of the Earth's position, but also allowed to use reference points of high reliability. And that allows us to shrink that cross-track, the minor axis of that ellipse. In this image, we come from your left to the right, from the west to the east. And so it is really navigation uncertainties that we see in the cross-track, and then aerodynamic and atmosphere uncertainties that we see in the major axis there in the long track. So to take it from the state of the art in the aughts and squeeze it down into that safe region at the bottom of Gale Crater, we had to use a piece of technology that we borrowed from Apollo. We used what's called guided entry. This was used when the Apollo astronauts returned from the moon, but there were pilots to override it if it went crazy. And this would be its first debut at Mars and its first use autonomously. So how do we do that? Well, we take a regular symmetric entry body. This is our entry body. And usually they come in sort of face straight into the wind. The axis of symmetry along the velocity vector, they develop just drag. We frequently spin them to average out any aerodynamic uncertainty or unevenness in the ablation of the heat shield. And to do that, and because of that, we keep very close track on the center of gravity and make sure it's right along that axis of symmetry. What we do for guided entry is we break that paradigm, and we intentionally place the center of gravity off axis. We don't spin the vehicle. And now, because the center of gravity is moved off of the center of pressure, there's a difference between the center of pressure and the center of gravity. That is an unstable position, and the vehicle pitches to find a new equilibrium position. At that canted flight in the new equilibrium position, we develop lift. And then we take that lift and we steer it back and forth, up and down in the Mars atmosphere to make sure that the acceleration profile we're experiencing as we're coming in is exactly what we anticipate. So if we show up and there are less molecules in the atmosphere of Mars at the altitude we thought there would be, or we've miscalculated the drag coefficient of the vehicle, we push that lift vector down and we drag ourselves deeper into the Martian atmosphere. We know that there are more molecules below us than there are above us, and we retain or recover the drag that we anticipated. That allows us to take a 150-kilometer major axis and shrink it down into something like 20. And it allowed us to make it down inside Gale Crater. Unfortunately, when we would get to Gale Crater, we'd be landing a rover that wasn't just your average everyday rover. It was bigger than your average everyday rover. So this is the rovers we've put on Mars, starting in '97 with the Sojourner rover on the Mars Pathfinder mission. She's about the size of a microwave, 25 kilos, about as heavy as my very heavy book bag. Pathfinder was a bit of a lark, actually, in some sense, because this was in the better, faster, cheaper days of NASA, and we were asking questions of NASA. Can we do things at radically reduced costs to what we think we might pay. If you go back to the days of Viking and you look at the amount of money that Viking spent, actually the beauty about the days of Viking is we didn't keep track of the amount of money that we spent. But if you go back and try and reconstruct what we probably spent in the Viking era to get to the surface, it's something in the $5 to $10 billion range. Well, in 1997 dollars, Mars Pathfinder put a little rover on the surface for $350 million. So that was an order of magnitude improvement and meant that we could do more of that. So we aspired to return regularly. We had some fits and some starts, but by 2004 we were placing twin rovers, Spirit and Opportunity, on the surface. They are solar powered, about the size of a coffee table. Actually, your round dinner tables are a very good estimate of what they look like with their solar panels deployed. Both of those used an airbag system. And more importantly, Spirit and Opportunity made a fantastic discovery. They proved that liquid water had been on the surface of Mars at one time in its past and influenced the geology, the morphology of the geological material that was left on Mars. Now, why is that important? That's important because here on Earth we know that where there is life, there's water. And when we find no water, we do not find life. And so the idea, hearkening back to this question of, is Mars alive? The idea that water had once been present in a liquid form on the surface of Mars was very encouraging. Now, unfortunately, Spirit and Opportunity could not teach us many things about the water, how long it had been there. Had it flown over the surface, had it flowed over the surface for 20 minutes, 20 days, 20 years, a millennia? Was it salty? Was it basic, acidic? In short, was that waterborne ancient environment of Mars habitable? Spirit and Opportunity could not answer that question. So enter Curiosity. She's packed, filled with all the instruments you'd ever want to answer that question of habitability of the ancient waterborne environment of Mars. But she is big. She's big by previous rover standards. She's big by any standard. If she were here beside me on the stage, I'd be dwarfed by her. She's bristling with equipment. That little pink monocle, you know, there's a great Rorschach test in Opportunity's remote sensing mast. You either see that she's a cyclops or that she's binocular vision with some weird hairpiece or a corsage in her hair. But that pink piece is actually a laser ablation spectrometer, so she can fire a laser at rocky material half the length of this room away, vaporize the surface, look at the vapor through that pink lensed telescope, and determine features of the mineralogical content of that material, and if she wants to then drive over there and actually do work. So she's big, she's bad, and she's really hard to land. So we looked at many different techniques to land Curiosity. We started with airbags. That's the technique that we used for that final touchdown system for Sojourner and Spirit and Opportunity. But airbags scale very poorly. They scale in general poorly. They're a wrapper around the outside of something. So there's a superlinear R-squared-ish kind of relationship there. They scale badly in stress. The bag's stresses don't scale well as the scale of the thing in the center goes up and as the mass goes up. In short, there is no material known to humankind, no fabric that we can make bags out of to hold air in to land a vehicle of this size. So So airbags was right out. We thought about legged landers, a la Viking. In 1999, we lost a pair of vehicles that were on their way to Mars, the Mars Climactic Orbiter and the Mars Polar Lander. And in the wake of that loss, in the analysis of that loss, we refamiliarized ourselves with how difficult it is to autonomously land a legged lander, a tripod-legged lander, on an unprepared surface. And we sort of well-defined what kinds of surface slopes we would be comfortable landing such a vehicle on. And they are not very slopey, 15 degrees, 10 degrees, kinds of slopes. When you put a 1-ton rover on top of that vehicle, it becomes far too tippy and far too intolerant of slopes, and so it was out. We tried to invent a new system. We tried to fix that tippiness by taking the legged lander and splaying the legs out, giving them 6 legs, wide, splayed legs, and allowing the propulsion system to come down in kind of intimate contact with the rocky surface. Now, the problem there is naturally explosion on touchdown is considered extremely poor form. So we needed to armor the propulsion system against the rocks that it might encounter. And as we went to armor that propulsion system, the mass cost of that technique ate our lunch. So it proved an evolutionary dead end. So then in the late summer of 2003, facing sort of dead ends in all of these 3 other architectures, a whole bunch of folks gathered together. People who had worked Pathfinder, who were in the middle of working MER, people who were working MSL at the time. We came all together, sort of the brain trust, the intelligentsia, the cabal of entry, descent, and landing. And we spent a brainstorming session over the span of 2 days, asking ourselves, is there something that we've missed? Is there an architecture or a perversion of an architecture that might work? And out of that meeting came this thing down here in the lower right. We called it direct placement. It rapidly got the name the Sky Crane. And we know from the beginning that it had a whole bunch of engineering features that we liked, and that it would make a major assault on our credibility to try and pitch this to anybody. But that's what we did. In fact, this is the slide I used when I was pitching it to Mike Griffin, the NASA administrator at the time, in January 2006. This was a long, sometimes slightly heated discussion about landing techniques, and this was the slide that I used to talk about the Sky Crane. Now, the Sky Crane has several things that we really love about it. First, I need to get some nomenclature out of the way. The Sky Crane is a maneuver. The vehicle on top we call the descent stage. It's the propulsion system. It's got sensors. It's got a terrain relative radar that does velocity and range. And it has an IMU, gyros, and an accelerometer. And it's got all the tankage and all the propulsion system. And the rover, which sits below, we call the rover. And when those two are together, we call them the powered descent vehicle. And we fly for quite some time with the 2 vehicles bolted together. And then just 20 meters above the surface, when we're in direct vertical flight, we lower the rover below us, and then the 2 vehicles continue down to the surface at 3/4 of a meter a second. Now, what does this mean to us? What were some of the engineering virtues? We liked the fact that the descent stage, where the propulsion and the GNC, the guidance and navigation and control were all going on, was well separated from the surface. That slope-related disturbances could not put moments onto the vehicle. With a legged lander, if I land on a slope, I get a moment. That pushes the vehicle to this attitude. The vehicle drives away the controller says, no, 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 I want to land. It turns, it goes back down, gets it again, and you can get this skittering. Here, all of the forces from the surface are tension-only, you can't push on a rope, tension-only forces that gather at the center of gravity of the descent stage. And we have little clock springs that allow the slack to be pulled in so that we can actually fly the descent stage virtually through the surface of Mars. So it comes down, the rover's weight's taken up, it still goes down. It keeps going down. And we don't measure a touchdown event, but we measure a post-touchdown state of the vehicle. Back when we were doing that analysis in '99 for the Mars Polar Lander, one of the leading causes of the loss of that lander was that when it deployed its legs prior to landing, 80 meters above the surface, it tripped a touchdown sensor, that because it was looking for that imminent touchdown event, it mistook that noise for the surface of Mars, turned off the propulsion system, and fell the last 80 meters. Is that a bummer or what? They got close, doesn't count. No, not much partial credit in this game. So we liked that. We liked that we sensed the post-touchdown state. We liked that the descent stage was insulated from the vagaries of the Martian surface. And we liked that we were using the rover's wheels and mobility system, which had been designed from the start to interface with the Martian surface and conform to the uncertain and unknown terrain. And we were using that to land on. Well, it was an hour and a half with Mike Griffin, and he had started by saying that he thought what we were doing was crazy, and he asked us to come on down, and thankfully, he took a moment to end and turn to the audience, the assembled folks, and say, I still think it's crazy, but I think it might be crazy enough to work. I think it's the right kind of crazy. So we'd done the numbers. We'd done the analysis, first on pen and paper, then in ones and zeros and computers, and everything looked good. Here's one of millions of simulations we did. This is on a 35-degree slope with very large rocks. Slope is so steep that the rover actually can't rove on a surface like this. And you can see her sliding downwards, but we can still land her safely. So we were buoyed by our analysis that anywhere the rover could rove, we could land her, and we could land her even in places that were more extreme than she could rove. Unfortunately, there was no test that we can conduct here on Earth that will teach us whether we're right or not. During those times when we were pitching this and trying to help hold on to a shred of our credibility, I developed a little pithy quote that I would say all the time, which goes something like this. Great works and great folly may be indistinguishable at the outset. So that's great. Unfortunately, so what that means is, genius can look crazy. Unfortunately, crazy also looks crazy. And so, I don't know, is this plug here, this little quarter-inch stereo, is this live? Can whoever's got the sound side of this bring it up? Certainly. Thank you very much. Give me a second. That's okay. I've got many. Get some clickety, clickety, clickety here with me doing this, if it's attached to anybody. It's going into this dude. Is there a switch on here that I might turn on? I'm going to turn on a switch. You hear that? There we go. All right. Let's play. So in case you weren't around last summer and didn't get a chance to read the newspaper, here's a sense of what happened.
Coming up on entry. Vehicle reports entry interface. At this time, it will begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. The vehicle has just reported via tones that it has started guided entry. Target at this time. We have seen peak deceleration. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Heat shield has separated. We're found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending. Standing by for batch shell separation. We are in powered flight. We're at an altitude of 1 kilometer and descending. Standing by for sky crane. Sky crane is started.
Single eyes, you remain strong.
Touchdown confirmed. We're safe on Mars. Curiosity will take us.
So that was a pretty good night. Infinitely preferable to the alternative that may have awaited us at Mars. So when you get the signals down, the numbers come in that tell you the vehicle's safe, it has much less meaning than these do. These are the first images from a new place on Mars, a new perspective on our solar system, the result of ingenuity of human beings. On the left there is the very first image from Mars. We had orbiters in radio link with the spacecraft as it was going down to telemeter data down in case we had a failure. We wanted to be able to reconstruct what had gone wrong. We were just losing that orbiter link, and we thought we might just have a chance to put one image down the pipe in real time, bent pipe through Odyssey. And that was that image. It's an image out of the rear has cams. They are fish-eyed, lensed cameras that are used to detect hazards during mobility. We shot out the rear because you remember we throw the descent stage away when we land. And because we promised the scientists we'd throw it away in the northerly direction, because they said they wanted to go in the southerly direction, we thought we were most likely to maybe, if we were lucky, see the cloud of the impact site of the descent stage as it flew away. Well, that, you'll have to sort of take my word for it, is in fact the impact, the cloud associated with the impact of the descent stage with the surface. We would later triangulate this, the descent stage location. We'd actually take images with this camera on the next pass. That cloud would be missing. So that's sort of our last piece of the landing event caught in the action. Here on our right is the first image with the clear lens caps off of what is, in theory, our final destination, the foothills of Mount Sharp. That's why we went to the surface of Mars, and this location was for, in those foothills, the scientists believe that they see signs of hydrated minerals. So these things provide the meaning to myself and my fellow team members. They really sort of hit home that we did it. And on the numbers, we kind of did it good. The turquoise there is that landing ellipse, that uncertainty footprint. And the spots there, the X is where Curiosity, the black X is where Curiosity thought it landed. The green diamond is where we thought it was going to land. And the red is where it actually landed, and they're all within a stone's throw, if you had a good arm, of one another. In fact, you know, we have that CG offset to develop lift, and we discard the weights that we use to give us that offset. And you may have seen that in the video. It goes chick, 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 and we toss off some tungsten masses. We even predicted where those masses would hit, and we didn't do such a bad job. Those little blue dots in that ellipse are where the masses are, and there's little black arrows that the scientists called out the impact craters. And as being that our garbage is useful as a science tool because they know the velocity of the impact, and so looking at the craters from orbit can actually tell them about the material that the objects impacted. We've reconstructed the trip to the surface, and largely it was excellent. If the pre-flight prediction was within one standard deviation of a normal pre-flight estimate, it's green. If it's yellow, it's within 1 and 2 sigma. And if it's red, it's greater than 2 sigma. And so there are very few red or yellow numbers. A couple down in the lower right, those are the result of engineering sandbagging. That's overly conservative models for our propulsion consumption, and as Ray will attest, and our radar performance and initial attitude uncertainty. But there is a number worth discussing. The 0.6 meters a second in the inset there, the touchdown velocity, was much, much lower than we thought it should be. We anticipated, or we commanded 3/4 of a meter, 0.75 meters a second. And we thought that to 99%, we would expect that to be within plus or minus 0.1 of that 0.75. So in Earth speak, between 0.65 and 0.85 meters a second is what we anticipated to within 99% or so. 0.6 is a lot slower. So what was going on with that? Well, late in development, we became concerned about the near field pattern of our landing radar. We had 6 beams on that radar, and we restricted ourselves to using only 2 once we separated the rover below the descent stage. And because we were only measuring 2 directions, or 2 components of velocity, but we were controlling our speed in the X, the Y, and the Z direction, we had to estimate one of those directions. We estimated Z. And we were confident, perhaps even prideful, that we understood the surface gravity of Mars well enough to use that as an estimate. The old saying, pride cometh before a fall. It ends up being that there's a gravity anomaly at Gale Crater that was not present in any of our models. The best of our models did not have this. And that gravity anomaly meant that there was less gravity by 400 microGs at the surface of our landing site than we had anticipated. And so as soon as we separated and we went down to 2 beams, we started to slow down. We had our throttle set to handle what we anticipated as the surface gravity, and the anomaly meant we were slowing down. Now, that was very convenient for us because landing slower is usually thought of as better than landing faster. And we had no brilliance or anything but luck that meant the sense of that anomaly was in the direction that it was. If it had been in the opposite direction, we would have landed at, let's say, 0.9 meters a second. And although, in my opinion, the rover would have been just fine, every time something went wrong with the rover, for the rest of the mission, the guys would turn around and say, oh, it's the EDL guys because they landed us too hard. So luckily, we're on the soft side. Nobody can come back and say it was our fault. But we got lucky, and we should remember that in our future expeditions. We've taken all sorts of great images of the bits and pieces, the naughty bits of EDL. Sort of in the middle of the larger image is Curiosity herself. seen blown up looking like a beetle in a little sort of gray, charcoal-colored cloud. That dark grayness is us actually cleaning the iron oxide-rich dust off the Martian surface with our rocket plumes. We can see the descent stage impact, that big dark splat. That's where the descent stage hit, where the packed shell and parachute landed, the heat shield, and other bits and pieces. Since landing, she's moved on out of what we would eventually name the Bradbury landing, where we landed after the author Ray Bradbury, and over to a location we call Yellowknife Bay, where she is doing some pretty significant science. An example of the success of exploration is when your plans are kind of overrun by that what you find. Our plan had been to move due south from the landing site to the foothills of Mount Sharp. And the scientists moved due east, 90 degrees at right angles to the plan. And they did that because they saw a junction of interesting colored material locally, and they wanted to see if there was anything worth scratching around in. Well, there was. And in that area, we have done the first of our cores. We drill down into the surface, down below the oxidation level, and into really old material, and pull up powder. You can see it there in the center image. It's gray, right? Not this oxidated red, but gray. An analysis of that material has convinced the scientists that, in fact, the primordial wet environment of Mars was, in fact, habitable for life. That if life had existed, or if it exists today, that ancient environment would have supported it. Now, we keep asking Mars to say no. We say, is there life? I guess it would be he doesn't say no. He doesn't say yes. He doesn't say, here's the life, here's the microbe, I got it. You know, there's a little green man smacking the rover in the face. But he stops short of the no, which encourages the next question, the next trip to the surface. So she's there. As the president's science advisor said, 2,000 pounds of American ingenuity sitting on the surface. And she's the result of a truly incredible group of people. Teddy Roosevelt is a great source of quotes, and I love this one perhaps more than any of his beautiful words. Far and away, the best prize that life has to offer is a chance to work hard at work worth doing. I firmly believe that. Thank you. I've added a version of it of my own, which is that great works require many people to work together, is another great prize that life has to offer. The fact that we can only accomplish these great things by working together, these social animals that we are, is fantastic. It's a gift to us. And we have a remarkable set of people to thank for this. From the principals, Alejandro Miguel San Martin, the GNC lead, and my deputy phase lead for EDL, a man who came from Argentina at 17 years of age, not speaking a word of English, but wanting to study to become an aerospace engineer and work at the Jet Propulsion Laboratory. And that's exactly what he did. And we couldn't have made it to the Mars without him. Tom Rivellini, the mechanical systems lead for EDL. Jeff Umland, my predecessor as the leader of the EDL system. These are the principles of the act of today, but we stand on the shoulders of giants of yesterday. Dare Sabahi, and Richard Cook, who were both very major characters in the Mars Pathfinder and MER systems. Rob Manning on the right, next to John Cassani, who I think probably for you guys needs no introduction. All titans who set the stage for us to be successful. And a whole legion of people, Devin Kipp, of young whippersnappers who were ready to get in there and kick some stuff. Devin Kipp, Alan Chen, David Way from the Langley Research Center. This was a multi-center event. This was not just Jet Propulsion Laboratory. We had all sorts of talent from around the nation. Steve Sell from JPL, Ravi Prakash, these guys are all young, right? They are the next generation. Jody Davis from the Langley Research Center, Ann Devereaux, JPL, Ben Sichi. I could keep clicking this until you couldn't see any more people. There's only 200 of us here of about 2,000 that really lent themselves to getting Curiosity built and safely on the surface. So it's a triumph of teamwork and of us being able to carry something that was so big, literally physically, and certainly intellectually, that it was bigger than all of us. And it took an entire ensemble to hold every little piece in their minds and speak and connect with one another so that we could eventually bring a tremendous rover to the surface of Mars. And with that, I'll conclude. Thank you.
There have been two adrenaline rush landings in my lifetime. One of them was Apollo 11, and that adrenaline rush was unplanned because the computers didn't work precisely as they thought they would. You gave us the second adrenaline rush, but you planned to give it to us. Yeah. So it is our great privilege and pleasure and honor to present you and your team with the NSS Space Pioneer Award. There was a certain irony here that it is a stylized moon globe, but it's basically a metal sphere, so from a distance it will serve for Mars.
Ray, you get some hands in there.
John, we got to work on a Mars replica here. Come on. Let's go over that one. Follow the director, please. Thank you.
We do have time for a few questions from the audience, so there's a portable mic.
While we're waiting, I rode down in the elevator with Adam, and I thought, wow, who's this hip young dude? I was reminded of Mott the Hoople, Ian Hunter, and all the young dudes. And that's who we have for rocket scientists right now. Isn't that amazing? You know, I had a vision of some older gentlemen receiving this award tonight. I'm really glad to see these young, excellent genius men here tonight. You guys are amazing.
Thank you very much. You can help me answer some of these questions.
Try.
This is Ray Baker, the propulsion lead for entry, descent, and landing. Those were his engines landing us on the descent stage. So, any questions? Yes, sir.
I was wondering if your team has identified any weight limits on the landing system that you devised.
Yes, architecturally, we have not identified a top, even architecturally you can go in either direction. There's nothing, we haven't explored it extremely, but we don't see anything that is a fundamental limit of the architecture. When we go to Mars with the Science Mission Directorate budget, which is fairly modest, you run into some hardware scaling questions because you don't want to design a new engine or something like that. But in terms of the architecture, we have not identified any limits.
Eventually, we would like to land man on Mars. So I see there are many corporations who are trying to land man on Mars. They claim that they can do so. So what do you think that the current EDL technology is good enough to land man on Mars in next 10 years?
You know, I don't think we really knew how we were going to land a man on the moon when we said we'd do it. So I don't take as a necessary condition, precondition to trying to get to Mars that we know exactly everything that we're going to do to go to Mars. I personally think I can think of several ways of doing it, whether they really are crazy or not. Great works. Probably crazy. Time would tell. But likely we'd have to omit. Remember we said there was 4 things that you needed to do? That parachute thing, that second stage of the aerodynamic decelerator, probably goes away. Because we know from Earth experience that dealing with and managing larger and larger parachutes gets very challenging. And to land, let's say, a 50 metric ton item on the surface of Mars, you'd need a parachute about the size of the Rose Bowl. And that's way bigger. We know that that's trouble already. But to do that means we're going to be lighting up our engines at supersonic speeds. And Ray, do you want to?
Yeah, so as you get bigger, the atmosphere becomes less and less of a contributor to your total energy reduction as you get from 13,000 miles per hour down to, say, a meter per second. So the propulsion system needs to take up more of the heavy lifting of that endeavor. And so I think that's where the manned systems will go, is more propulsion toward the end. Supersonic retropropulsion is certainly a part of that. We also have some inflatable aerodynamic decelerators that we're working on to try to get as much bang for the buck out of the atmosphere as we can before we get to the ground. So the great thing about Mars is, you know, we've done it several times, but we've only done it a handful of times in a handful of ways. We don't know the best way to get to the surface yet, and that's part of the problem that we have to solve going forward.
In exploring the future, the extremes of the Martian environment, I'm curious if there are any future plans to go to the Martian polar ice caps, and then also if there's any future plans in the works to go to the Martian Grand Canyon, because last time I was at the Colorado River, it was teeming with jet skiers and bass. So I'm really curious about that.
I don't think there's going to be jet skiers in Valles Marineris. No. So the current projects on the books to go to the surface of Mars are InSight, which is a relatively low-cost reflight of the Phoenix lander, which itself was a reflight of the Mars 01 lander. And that will go to, I believe it's an equatorial region, and its main focus is to place a seismometer on the surface. So it's not going into the polar region. The polar region is very tough. You need to have, from an energy perspective, you can't be solar at those high latitudes. Or you can be solar during the summer, as Phoenix was, but you have absolutely a known lifetime because the sun will set and you will die. The second is Mars 2020. It's just called Mars 2020 now. It's a reflight of Curiosity, in large part, using the Sky Crane landing system. A different payload, we imagine, and what that rover is going to do scientifically and what payload it's going to take is being discussed by science definition team as we speak. And so this summer, the science definition team should inform all of us what they want to do with a king-size rover on the surface of Mars in 2020.
Thank you for your talk. I'm glad the gravitational anomaly didn't go the other way.
Yeah.
Is it time in the near future that we actually need to bring Maria Zuber's team back and actually do a Mars Grail and get a better gravitational map of the Mars cons?
Yeah, that would be good. We had a pretty good map, actually. And, you know, sadly, in hindsight, there was a better map on Earth, just not a U.S. map. And that model would have told us about 300 micro-Gs of the 400 micro-G. Really what we should be doing is measuring. If you got 3 things you got to do, don't skimp. Do them, right? So we needed to measure 3 degrees of freedom. We should have measured those 3 degrees of freedom. Should we be doing a Mars global, gravity survey of Mars? I'm totally down for that.
At the Oregon Museum of Science and Industry that night, we had 1,000 people watching your landing. And when you had touchdown, we were jumping up, throwing chairs around, just going crazy. And when we got the first thumbnail, people were crying. So what I want to know is why you folks were so staid and undemonstrative relative to us at JPL.
Well, it's very interesting. There are many reasons, starting probably, well, we jumped up and down a lot, but only once we knew we were safe. We had a job to do. Really, the job is mostly sit around and watch, just like you guys, because it was all autonomous, and it all happened actually 13.8 minutes earlier. So we were all along for the ride. But we have a job to responsibly watch the data and understand what's coming down as it does. But what you mentioned actually is a very important wrinkle to all of this that I didn't really appreciate until landing night. I have a great image of about several thousand people in Times Square, and now for us on the West Coast it was 10:30 on the 5th of August, but for the East Coast it was 1:30 in the morning on the 6th of August. That's a Monday. It's 1:30 in the morning on a Monday morning, and there's thousands of people in Times Square watching the event unfold. And they're not there, I don't think, because they're dying to know about the pH or the salinity of the primordial aqueous environment on the surface of Mars. They're there for some other more human shared experience. And I think that throwing of the chairs around, I'd love to see a video of that, by the way, is an expression of the ape-like glee that we experience collectively when we become more. And I think when we explore, we become more. And so we all shared that. And in retrospect, I've started to believe that extension of ourselves, that just engaging in our wonderment and wonder and curiosity is a good enough reason to do this, even if we don't have awesome science questions or awesome science answers that come out of it. Exploration for exploration's sake is a very human thing.
Yeah, I have a technical question. Everything made engineering sense, other than it being crazy, except that I did not quite understand how you could detect the quasars on a craft that small.
Oh, no, we don't. We do it from Earth. It's a way of truing up our radiometric assets on Earth. Not only looking at the spacecraft, but they have essentially other points of reference. The quasars are other points of reference, rather than just the Earth's position and our ephemeris of where the Earth is, and our ephemeris of where Mars is.
Okay, that makes a lot more sense.
Yeah. No, we don't. The Earth tells the spacecraft where it is in displacement. The spacecraft tells itself where it is in attitude, because Earth can't do that. So we've got celestial sensors, and the spacecraft loads its attitude in, and both are very important to get to the bottom of the crater accurately.
Who did that amazing film, 7 Minutes of Terror, and whose idea was to do it? Because that's what I think captured everybody's imagination, to sit there along with your team and see what was going on and be so excited.
Right. So his name is John Beck Hoffman. He's a good friend of mine. It was his idea to do it. So actually, if you look back in YouTube annals, you'll see something called the 6 Minutes of Terror. 7 was the new 6, or the new 11. 7 was the new 11. But the 6 Minutes of Terror was something that he did mostly for the team back in MER, for fun. It was his idea, and we all watched it. And I don't even really, in 2003, I don't even know if YouTube existed. I don't think it did. I don't know if it did, but it didn't exist in my noggin. And we all looked at it, traded it back and forth on CDs and looked at it. It was a way of it was like a home movie. And then for the Phoenix lander in 2008, they liked that idea and they asked somebody else to do it. And they made one. It doesn't do anything for me. And for MSL, I went to John. I say, John, we need to do a 7 Minutes of Terror, because 7 is the new 11. Again, thinking about the team, right? It's a way of lots of us getting on camera and people going, oh yeah, look at you look like a dork or whatever. See, you said that wrong. That's the wrong unit, or that's the wrong value. All that kind of fun stuff. And so he went away and he came back and he said, well, his boss didn't want him to do it. So he asked me if I would help him put a rough cut together. So actually all of my own stuff in that came from that rough cut. And the people said yes, they'd like it, and we added some more team members, and it is. So it was his idea. He actually was going for something that he started going for something in a direction that didn't end up. It's all good art is like that. He had this idea of the movie Inception. Yeah. And so we were doing a sort of a film noir thing. It was at a lunch hour in the TV studio. He thought he was going to have a Sam Spade kind of backdrop on the green screen behind me, and so I was trying to channel Sam Spade there, and as it came to pass, he came up with these great graphics, and anyway, it went in a different direction, and the bosses weren't necessarily media savvy, but they were savvy enough to realize that they had something when they had it, and they put it out there, and it did have a big effect.
I truly believe that landing on Mars is such a great accomplishment for mankind. However, I would like to ask you, is there a possibility, knowing the Mars surface and just barely touching on it right now, is there a possibility of sending more robots and supplies, moving the rocks aside, building a little airstrip, and sending a drone up there, and then building into larger aircraft that would work with the CO2 in the atmosphere?
Yeah, absolutely. You can keep putting stuff on the surface of Mars and grow an infrastructure, and there's nothing that limits us from doing that except for financial concerns. And yeah. And whether that's the right thing to do or not is for all of us to figure out, the people of these United States.
We thank you.
Thank you very much.
Well done.
Thanks for the adrenaline rush. Thank you for introducing the phrase 7 Minutes of Terror into the popular lexicon. Thanks for the Mohawk haircut. Okay, we're not quite done yet. This ISDC is almost over, but we know that there's another one coming up next year, don't we? Do we all know where it is? Los Angeles. All right, Pat Montour, come on up. Pat is having her 4th go-around as chairman of an ISDC, which is proof of something. We don't quite know what.
We have to switch laptops.
Okay.
Put the arm down. Just need balance.
think you can help me with that one. It's going to be hard to follow that. Shouldn't slam it. What?
Turn off.
Pardon?
You turn off.
I build, or I used to, till a couple of months ago when I got laid off. I used to build satellites on a computer, but that's as far as it goes. I can build a satellite, but I can't run a PowerPoint. Well, the stuff I did was more artistic. Yeah. There's.
Do you want the mic?
Hmm?
Do you want the portable mic?
Because I can't reach that one. I can reach this one. Is it working? Hello.
We got it. Turn off.
Well, we hope to have more than that next year. I have a good buddy, John Spencer, who's going to be doing our programming. He's got a lot of things that he's planning. He's planning to tap into the entertainment industry, and he's planning to tap into the spacecraft, space science, JPL type stuff. So it's going to be a very variety type of program versus, just strictly hardware and that kind of stuff. He's tagged it as a space renaissance. We're getting close.
Yeah.
I worked so hard on these 5 slides. If it wasn't for bad luck, I'd have no luck at all.
Don't worry, we're still on time. We're good. We're good.
Well, I can be done. Thank you. No, that's not it. There it is. Now, how do I make it go? Okay. Thank you, yes. We're calling it the Space Renaissance, as you can see. It's at the LAX Gateway Hotel across from LAX, obviously. May 14th through the 18th. We've got some plans for some good tours. Haven't just got them settled yet, so can't really say what they are. We're hoping to have our gala under the Endeavor out at the Endeavor Center. Yeah. They took me for a tour out there, and it's like you're going like, oh my God, it's huge. You don't get that kind of a sense until you're standing under one. Let's see. And the reason we're calling it the Space Renaissance is because John felt that that really is what LA is. We're surrounded by science and the new entrepreneurial type commercial space. We've got a little bit of everything there. And we're getting closer and closer to working and living in space. I don't know why I threw that slide in. Oh, and we're planning on having a fashion show. This is a shot from one that they put on for the California Space Authority. Of course, they went out of business shortly thereafter, so I'm not sure that's a good idea. Maybe it was her. I don't know. It could be. It may have just launched itself or something. I don't know. But point being, we're looking at the arts, too. We're going to have a nice art show and hopefully a fashion show. And Moon, Mars, and LA in 2014. Thank you very much. Ronnie, when can we register? He says he'll have the splash up tomorrow. Yeah, and all you have to do is log in to nss.org and it will have the early bird registration until the 21st of June, or the 30th of June. Okay. Last day in June, whatever it is, you know.
Other questions for Pat before she takes off the stage?
I don't answer questions.
You don't have to answer
I'm not that smart.
All right.
Smart people answer questions. I rest my case.
All right. Thank you,
Although there have been guys with that jacket, that white jacket, following me around.
All right. The children have gone to bed. We're the grown-ups in the room. None of us here haven't been here for a long time. Very few of us. There's a few newcomers here, but you're part of the family now. So as longtime members of the family, we can tell the truth to each other, which is that this year for NSS has been a little bit bumpy. We don't have an executive director right now. We're not going to have one for a while. That's okay, because NSS is composed of a whole lot of very bright and dedicated people who keep the organization going. We've had rough patches before this. We're still here. We're still going to be here. And the reason we're going to be here in large measure is because we've got a lot of excellent people, and some of them we want to give awards to tonight. So for our Excellence Awards, I'm going to call up Dr. Stan Rosen, the Vice Chairman of our Board of Directors.
Good job with this group, Dave. Pleasure to see everybody tonight. We've got some very good people in the audience tonight, some notables, and we'd like to recognize a number of those who have done an outstanding job for NSS. Adam and Ray, congratulations. Congratulations to your team. I don't think you're going to find a more appreciative group of people than you found in this audience tonight of what you and your team have contributed to the exploration of Mars. But I was especially impressed not only by your managerial expertise and, of course, your technical brilliance, but by your ability to explain the significance of what you did, both in technical terms, in scientific terms, and in human terms, why it's important to explore and why what you did fits in with the history of humanity. I'd like to give you one more hand for that. Look, NSS is all about communicating, telling the story that you're telling the story that people need to hear about the importance of what you're doing and what we're all passionate about. Keep the spirit alive. Keep getting out there and telling that story, because that's as important as anything you're ever going to do. We'd love to have you do that. So congratulations again. Speaking of people in the audience, I would like to at least follow up on the comments about the NSS leadership and introduce some very important people to you. Yes, I am the vice chairman of the board, recently named, and look forward to being able to help out in that capacity. But I'd like to also introduce to you my comrades on the board who you've elected, for the most part, those of you who are NSS members. Most of our board members are here tonight. I'd like you to get a look at them. I think there's enough light in the room that if I introduce them and ask them to stand up, you'll be able to see who I'm talking about. First of all, the chairman of the board, Kirby Eichen. Kirby is here. Thank you, Kirby, for your leadership. Our at-large directors, Larry Ahern. It's hard for me to see, but Larry is in the back. Okay, thank you. Larry, thank you. Dale Ammon. Dale Ammon. Dale's here. I know he just got asking a question. Dale was just asking a question. David Brandt Erickson is not here, but let's give him a hand anyhow. He's listening. Anita Gale is here for the meeting. Is Anita here tonight? She had to leave tonight. Anita Gale. Alice Hoffman, I believe, is here. So Alice, come down. Over here. Yeah, thank you. We've also got Jeffrey Liss. I know Jeffrey's here. Right here. Karen Mermel at the front table. The president of NSS and a member of our board of governors, Ken Money. Ken's been here all day right there. Our Senior Operating Officer and Senior Vice President, who's not here tonight, Bruce Pittman. He just had to leave. Let's give him a hand. Our Treasurer is Joe Redfield. I know Joe's been around right here. I don't think Jesse Clark is here. Am I wrong? Let's give a hand to Jesse Clark. He couldn't make it tonight, though. Robbie Gaines. Haven't seen Robbie. Okay, give a hand for Robbie. Okay, Al Globus. Al has been here all week. Where is Al? Right standing here. Thank you. The chairman of our executive committee, Mark Hopkins. I don't think Candace is here. Candace Pancannon is not here, but let's give Candace a hand. John Strickland, I believe, is around. John, aren't you here? Please stand up and be recognized. Lynn Zielinski, right here at the front table. Lynn, please. Not here tonight, but you heard Pat talk about John Spencer. Let's give John a hand. And John's comrade for next year's ISDC, Pat Montour, who you just met. Pat, once again, thank you, on our board. Chris Carson is here, right? Where's Chris? Right here, standing up. Take a bow, sir. Bill Gardner's been here all week. Bill, are you here tonight? Bill Gardner, give him a hand. Peter Schubert. Is Peter here? I know he was at the board meeting. Give him a hand. And you've got one round of applause left for Howard Bloom. I've already introduced the fact that I'm on the board. That's right. Now, I'm here tonight to do something very special in addition to introducing you to your board of directors. And that is to share with you what we're going to recognize some people for the NSS Award of Excellence. This is our opportunity to recognize the fact that the people that you've just met and many others are volunteers. They don't get paid for what they do. They put in many hours, as you know, making things that help NSS be successful work. And in doing that, they give a lot of themselves and give a lot of their families, their time, their money, and their energy. But some of these people stand out especially, and we're here to recognize several of those people tonight. And when I call your name, I'd like you to please come up and be recognized so I can explain what you've done. The first honoree tonight is Dr. Don Flournoy. Don, would you please come up? Do I see Don? Mark, is Don here tonight? Don't know? Okay. If Don is left, we will go to the next awardee, and that is Dave Dunlop. Dave Dunlop here tonight. Not here. All right. I'm going to try again until I hit one, because I know that Karen Mermel is here. Karen, please come up. Karen is an absolute spark plug in everything having to do with NSS, and I could spend a lot of time today telling you about her bio, et cetera, but she is a professional project and program manager. She's worked in many industries in the information technology field, and she got her MBA at Lake Forest School of Management. But most importantly, she's been with this group since the early days of the L5 Society, one of our predecessor organizations, and she's been a member of NSS ever since. She's had many roles for NSS. She's been our Vice President of Public Affairs. She's been often on our Board of Directors and still is on our Board of Directors, as you now know. She's been our Chair of Strategic Planning, and one of her favorite jobs has been the liaison to the NSS Board of Governors on occasion. And she's been on many committees and represented NSS on National Public Radio in Chicago, where she's from. Currently, Karen is busily engaged, as you know, in leading our fundraising activities, trying to keep the wheels turning for NSS, and is in charge of our outreach activities, communicating to not you and not to me, but to everybody else in the world, and that's a big job in itself. I told her this afternoon she's doing the job of about 14 people right now, and she never gives up. So we appreciate, Karen, very much what you're doing, and award you the NSS Award for Excellence for 2013.
Thank you very much.
Now, get a picture of her. She wants to get your picture. And now, wait a minute, don't run off. You're never at a loss for words.
I'm not.
Come right up here and say a few words.
Well, the few words are, give me your envelopes full. Thank you very much. Thank you, everybody. I used to be able to do the job of 20 people, but that was about 30 years ago.
Our next awardee I know is also here tonight. Cliff McMurray, please come up. Congratulations.
Thank you.
Cliff has done also a number of outstanding jobs and played many roles over many years with the National Space Society. He's been the executive vice president. He's chaired the policy committee in that role. He was charged with the development and publication of NSS positions on many aspects of national space policy. He's been a real activist at the chapter level for many years. He's been the chairman of a prior International Space Development Conference like this one.
My wife, not me.
Okay, that was Claire. Claire takes
I was just the power behind the throne.
The motivator. And you've read about and read many of Cliff's articles in Ad Astra magazine, a frequent contributor. So Cliff, we recognize your accomplishments and thank you again for the NSS Award of Excellence.
Thank you. I think that the most, in my mind, most important thing that I try to do for the Society currently is chairing the business track for ISDCs, and I've been doing that for the last few years. Because if our dream is, in fact, men and women living in thriving communities, living and working in thriving communities in space, they have to have jobs to do. And it is, I think, important for more people to look at the business track, because that's where those jobs are going to be generated. I know I've been around this thing for longer than I can count, and I've seen a lot of pretty slides. And most of those slides have never gotten built because the people who had those pretty slides didn't learn how to do business. So come and see us on the business track sometime. That's right. We do have one more. Hang on. Well, we did have a Laurel and Hardy routine planned, and I see it's going pretty well so far. Stan, come on back up here. So, Dr. Stan Rosen, as you know, is vice chair of the executive committee, the chairman, vice chairman of the board. But before that, I got to know him as a calm and steady and reasoned voice on the policy committee. He's also involved with our strategic planning committee, and I'd like to tell you a little bit about him here. With no light, that's good. Stan, I can't do it. I'm sorry, the print's too small.
You're fine, you're fine.
God love you. Thank you so much for stepping in at this particular time with greater responsibility on the board, and we look forward to your continued calm voice.
Thanks, sir. Get a picture. Thank you.
Next time you all ask us to do this, make the print bigger and give us a light behind the stage.
Now, I've said enough tonight. I don't have anything else to add, but you do have one more award to give. Am I not right?
I don't have it to give, but Mark Hopkins has an award to give. Come on up, Mark. I was trying to think how to introduce Mark. I could perhaps do it the way that Arthur Clarke introduced Isaac Asimov, saying that introducing Isaac Asimov is like introducing the equator. Which year by year Mark comes more to resemble, but that's not true because it's really more my case that I come to resemble the equator. But Mark's been around from the beginning of this organization, and he's here to present the Space Activist of the Year Award.
Well, thank you, Claire, for that kind introduction. Claire, I have to disagree with you on a little thing. You came up here and said that NSS had a bumpy road. And I say, to hell with that, we're winning. The foundation of our strategic plan is to push certain key ideas to society as a whole, and such as vast majority of the resources of the solar system are in space, space solar power, space settlement. And the fact that we are winning was made very clear on Friday night when former President of India came here and said things that we'd been saying much longer than he had. When people like that start saying what you've been saying, that means we're winning. Now, one of the key reasons that we're winning, oh, by the way, see, this is an energy drink. And the reason this is important is because I've discovered in the past with regards to ISDCs that the better the ISDC, the tireder the people are at the end of the ISDC. And so I brought up an energy drink. Now, getting back to the real thing, we give this award, it's our premier award. It's the Chris Pancrantz Space Activist of the Year Award. And the reason that it is called the Chris Pancrantz Space Activist of the Year Award, why it's named after him, is because during a rough time, much rougher than anything we have suffered currently, which we haven't suffered, he was CEO. We didn't have an executive director, and so he had to do that too. And he did this for about a year. And we found out towards the end of that year that something he knew from the beginning, but hid quite well for a while until it became obvious, that he was dying from cancer. Chris Pancrantz believed strongly in the goals of the society, as indicated by the fact that he spent the last year of his life on this planet dedicating himself to our goals. He strongly believed in the space movement, in space settlement, and that the vast majority of the resources of the solar system lie in space and can be used for the dramatic betterment of humanity. We are winning because of people like Chris Pancrantz. This award is given partly because of the success of whatever somebody's doing, but mainly because of dedication in the sense of Chris Pancrantz. This year's winner is particularly apropos in the sense of Chris Pancrantz. She is a former teacher, just retired. She has an MS in physics. And I know something about teaching. I've got some insight into that because My mother was a teacher. My father was a teacher. My wife's a teacher. My daughter's a teacher. Miss me somehow, but anyway, this particular individual is really amazing as a teacher. Let me just give you some of the ideas, and I've listed some of the awards and honors she's given here, which are just a small portion of the total, if you ever look at her resume. She is a NASA Galileo educator. She is a NASA JPL Solar System Ambassador. She received the NASA Student Involvement Hall of Fame Award. She has received the Candy Technology Scholar in Science and Technology Award. She received the Christy McAuliffe Fellow, that's the teacher that died in Challenger accident. She received the Presidential Award for Excellence in Science and Mathematics and Teaching. She has received the John F. Kennedy Award for Courage. Now let's tell her about what she's doing for NSS. She's currently chair of our projects committee. She's chair of our education committee. And quite interestingly, you seen all those students running around at the conference? Before Lynn Zielinski took over the role of organizing those students, we got maybe at the most 20 such students to come to the conference. And now we have on the order of 300. Lynn Zielinski is also our Vice President of Public Affairs. And once she was a pilot, and at that time she was on the fast track to becoming an astronaut. And due to a plane crash, her vision would no longer allow her to be an astronaut. But NASA's loss was the gain of NSS. Today, she is here because she is one of the people of why we are winning. Let me bring forth Lynn Zielinski. To know whether she really has to, and the answer, talk, and the answer is yes.
Yeah, do I really have to talk? I've been talking all weekend, all weekend to the kids. I've been using my teacher voice for everybody. You know, there are many roads to space, and on that road, the many roads, there are many people, and you meet many people along the way. And when you meet those people, you embrace them, because by embracing the people, you can move forward along that road. And sometimes there are big people and little people and really teeny people. And there are children and there are adults and there are old people. And the interesting thing about the people is they're so interesting. And in the many walks of life on the many roads to space, we are all part of the people that make up this organization, which has been around for a very, very long time. And you're an amazing group. And I really respect and honor each and every one of you in many, many different ways for many, many different reasons. And I want to thank you.
I get my energy drink, so.
I don't believe I ever said that we weren't winning, did I? Bumpy road, yes. We're coming to the end of another ISDC, and as Mark would say, one of the signs that we are winning is that in spite of the bumps, we have this ISDC, which has been quite magnificent, don't you think? I would like us all to give Dave Dressler a hand. So once again, we came together as a family for our family reunion. We've just got one more day to go, so let's go out and party as hard as we can until it's all over with.
Thank you, Cliff. What a wonderful MC. What do you say, Al? Give Cliff a hand. Thank you, Cliff. I'm truly honored to have this privilege and bring phenomenal people together for the celebration. But like Cliff said, the party ain't over yet. We got a big one going on in the ballroom tonight, and I want to see every one of you over there because it's rock and roll time. We got rock stars. They didn't bring instruments, but they brought spacecraft. You guys are my rock stars, all of you. Celebrate.